So earlier we learned all the prerequisite knowledge that is needed for the chapter rational numbers. First we learned about natural numbers which start from 1, 2, 3 onwards. Then we learned whole numbers which start 0 onwards, 0, 1, 2, 3, 4 onwards. And then we compared the natural numbers with the whole numbers. And then we learned some things about integers and how it is a superset of both natural numbers and whole numbers. So we learned that integers are a superset of natural numbers and whole numbers. Then we learned what we learned in 8th grade about rational numbers. So we revised that rational number is represented by q and it is supposed to be expressed in p by q form. So it covers many decimal numbers.
Yes.
So these decimal numbers have either a terminating decimal expansion or a non-terminating repeating decimal expansion. We'll learn about it further. So the only criterion is that the numerator and denominator must be integers, and as usual a denominator in a fraction cannot be 0. So q cannot be 0. So p is an integer and q is a non-zero integer. Later you and I gave some examples.
Yes.
And now we are going to cover a new topic. So before we introduce ourselves to this topic, I'd like to ask you one question. Let me draw some Costco balls here. This is one Costco ball here. This is another Costco ball here. Okay.
Yes.
Your friend Shyam has two Costco balls.
Yes.
And I have 3 Costco balls like this.
Yes.
I hope I'm doing the correct one. Okay. So now my question is, how many, what will we get? Will we get a bat? If we add 2 Costco balls, will we get a bat?
No, sir.
No, definitely we will not get a bat. Will we get a flower?
No, sir.
If we add balls?
No, sir.
No, definitely not. We are going to get in the end the Costco balls itself.
Yes, sir.
How many Costco balls do we get here?
So 5.
1, 2, see, 1, 2, 3, 4 and 5. So we get 5 Costco balls. The most important thing is that Costco ball and another Costco ball. I hope you know that yellow color tennis ball, no? You would have seen,
Yes.
yeah, with a white strip. Okay, so that will also give you another Costco ball. It will not give any other type. So the type remains the same. The type,
Remains the same.
yes. So remains the same. Now we know this.
Yes.
Can we extend this idea? I am saying, can we extend this idea to mathematics? If I say I have a natural number,
Yes.
I have a, so let us start off. I have a natural number and I add another natural number to it. Natural number to it. What would I end up with? Would I end up with a whole number? Would I end up with an integer or some other sorts? No, of course they are integers also, but in particular we will end up with a natural number. So let us verify this. Let us do a bit of a verification. And we can try to find some exceptions if you can think of. Can you suggest a natural number for me?
So 3.
3, okay, good. And one more?
So 5.
Okay, alright. Which is equal to?
8.
Okay. Now we are looking at the type.
Yes.
Alright. So what type is this? This is a natural number. And this is also?
Natural number.
Definitely. And this also hopefully, yes, it is a natural number. So we can say the type has not changed over addition. And this particular conservation of type, that is the type remains the same. This is not always the case.
Yes.
As we will discuss many operations, this will not go as smoothly as in addition of natural numbers. Thankfully, we have got
Some question.
yes, we have got natural number again. So we can say that natural numbers are closed over addition. Closed over addition. So this new word which we have figured out just now, closed. This is called closure property. Closure property. What does closure property say? Okay, so closure property says that, okay, so we'll do closure property over addition now. Let's be very specific. What does closure property over addition say? If we add two numbers of the same type, Costco balls, okay,
Yes.
of the same type, the sum is also of the same type. The sum is also of the
Same.
yes, same type. Let's try to extend this idea to other types of numbers which we have already done as we are checking. So we have verified. So we have our first conclusion that yes, natural numbers are closed over addition. Shall we check for next one would be whole numbers?
Whole.
Yes, let us check for
Whole.
whole numbers. So here let me go and write whole number, write a short form, plus whole number is equal to whole number. Let's verify that. Alright, and so we know closure property over addition. So let us pick some whole numbers. For the sake of including whole numbers, what is the difference between natural number and whole numbers? Can you tell
Whole
me?
number is starting from 0.
0. So it has one extra digit. Let us use that.
Yes.
Okay, let me use a 0 here and I use say 2. Okay, 0 plus 2 is 2. And definitely this is a whole number. And this is also a whole number. And this is also a whole number. We could try another example also. Let's not limit ourselves to just 0. Any other whole number would be just like natural numbers. Let's say 2 and 5 gives 7. Of course, this is also a whole number.
Yes.
And this is also a whole number. And this is also a whole number. We can clearly create a statement like this. B, and we can write, can you change this to whole numbers and tell me the statement?
Yes, sir.
Whole
numbers are closed over addition.
Very nice. Whole numbers,
Are closed over.
yes. It's as simple as that.
Yes.
Whole numbers are closed over
Addition.
addition.